Hello, lovely 3H students. Today we are going to talk about how we can write the equation of a function when we're given the graph. So the first thing you need to get comfortable with is identifying the shape from a graph. So if we look at a function like this, I clearly have an end point down here. That's going to be my locator point. And a function that has an end point like this and curves up, it kind of looks like half of a sideways parabola, is a square root function. This is a square root function. Okay, so what is the locator point? Well, in this case, that's going to be the end point. So that appears to be at 4, 2. And then we need to figure out the a value. So again, you're going to refer to the mother function on this. So if we have the square root of x, the most basic version of a square root function, and we plug in a value, we can figure out what the expected value out is. So if I plug in 1, for example, so if my input is 1, I expect to get an output of 1. So normally we would go over 1, up 1. So let's see what we do in this case. We go over 1, up 1, over 1, up 1, 2 to get to the next point on my graph. So we went over 1, up 2. So what we're doing is we're multiplying our output here by some a value that's going to turn my 1 into a 2. So my a value must be 2. 1 times 2 is 2. All right, so now we need to write this in graphing form or vertex form. So remember, for a square root function, that's going to be in the form of a times the square root of x minus h plus k. Again, following very similar format to all of our functions, we know that our a value is 2. We know that our h value is positive 4, so it's going to look like a minus in here because we're subtracting our h value. And then we also shifted up 2. So that is the equation, that is the equation of our graph there. All right, next, something that looks like this and curves, okay, is called a cubic function. So we're raising this to the power of 3. Again, that's why we get the positive. It grows faster than a quadratic because it's now to the power of 3. And then we also get the negative version because cubic to the power of 3, we can get negatives out of that. The locator point on a cubic function, first of all, it's a locator point. And so is this one, is a locator point because it's not a vertex. So the locator point on this one is that center portion where it starts to curve. So our locator point in this case is at 5, 4. Okay, again, when we're trying to figure out the a value, we want to think about what input we would give the mother function and what output we would expect, and then determine if we need to multiply by some a value. Okay, so the most basic version of a cubic function is x cubed. So let's look at our graph over here. Looks like if I go over 1, I don't land at a nice whole number on my graph, so I don't want to do that. So I'm going to go over 2, because it looks like up here at 1, 2, 3, 4 up, now I have a intersection point there where I can see my function crosses nice whole numbers. So you're always looking for nice whole numbers to make your life easier. So if normally we give our function an input of 2, we would expect to get 2 cubed out, 2 times 2 times 2, which is 8. However, we got 4 out. So we multiplied by some a value, and we got an output of 4 instead of 8. So what happened was we cut our output in half. So our a value must be 1/2. Okay, so again, we're looking for a, this time x minus h cubed, because this is a cubic function, plus k. Our h value is 5, our k value is 4, and our a value is 1/2. 1/2 times x minus 5 cubed plus 4. All right, when we see a V shape like this, we know it's an absolute value function. And we're looking for the vertex point there, which appears to be at -1, 0. So we're shifting left 1, not up or down at all. My k value is just 0. And now I have to determine the a value. So the most basic version of an absolute value function is just the absolute value of x. So we're looking for our x and y inputs. So let's see what we have here. Over 1 goes up 1, 2, 3, 4. So if I give my function an input of 1, normally the absolute value of 1 is just 1. However, we're multiplying by some a value and we're getting an output of 4. So our a value must be 4. Every output is being multiplied by 4, stretching it out. That's why it looks so tall. All right, so a times the absolute value of x minus h plus k would be a vertex form for any absolute value. And now we're just going to plug in our values. 4 times the absolute value of x plus 1, because it would be minus a negative, so that's a plus 1. Different from my absolute value symbols here, but I'm floppy writing, so there you go. And then plus 0, which I really don't need to write. No mathematician is going to waste the ink to write plus 0, so your answer is done right here. Okay. All right, we know that when we get these two curvy business things happening here, this is a rational function. And our locator point is the intersection of our asymptotes. So if you look at where these curves are approaching but not touching, that's how we find our asymptotes. So we have an asymptote right here. It looks to be at -3, -1. So that is my locator point, -3, -1. Again, the locator point on a rational function is going to be the intersection of your two asymptotes, your horizontal asymptote and your vertical asymptote. Okay, to determine a, remember a is like that distance from the center there. So if it looks to be pretty similar to our normal mother function, then it probably has no a value, or rather not no a value, but an a value of 1. So diagonally from the intersection of the asymptotes to that curve, we went over 1, down 1 here, and left 1, up 1 here. Okay, so normally we would go over 1 if a rational function, the most basic version is 1 over x, okay? And then we have our x, y value. If we plug in 1, we normally get out a positive 1. So normally when we go to the right one, we would go up 1, but we didn't, we went down. So what I know about a, I only went down 1 though, so I know that a is just a -1. So what's happened in my curve is shifted, reflected because of that negative a value. But the distance from the intersection of the asymptotes is standard, so there's no stretch or compress. We're just flipping. All right, so now we need to put this in the form of a times x minus h plus k. Okay, our a value is -1, so -1 over x plus 3. Again, keeping in mind that the value of the asymptote or the value of x that breaks this function, creating our asymptote, is -3. So we have to have a positive 3 in the denominator. Again, minus a negative is a positive, and then -1 because we also shifted down. All right, hopefully we all know the shape of this is a quadratic, or you could call it a parabola. This has a vertex. Oops. Oh, come on. Vertex. This one has a locator point. This one has a vertex. Going back to those, sorry about that. Okay. All right, so on our quadratic, we have a vertex here. It appears to be at 0, -4. So my locator point is at 0, -4, or my vertex rather. Also a locator point, but specifically a vertex because this has a vertex, a max or a min, right? In this case, a max. And my a value. All right. So normally I go over 1, down 1. That's definitely not happening here. I'm just looking for whole number intersections again. So I'm looking for that one right there. So this is over 1, 2, 3. And normally, okay, so if we have normally x squared is our mother, and we have x and y. If I give it an input of 3, I expect to get 3 squared out, which is 9. However, I did not. When I went over 3, 1, 2, and 3, I went down only 1. I went down 1. So I want to multiply this by something that's going to give me an output of -1. Are these going by? Oh, no, 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 for now. Look at the scale. I'm so wrong here. Try again. Okay, let's start over. Let's look at our scale because I was getting messed up by my scale. Okay, so notice this is 1 right here. So I did not even go over a whole 1. I went over some random fraction here. We don't want to do that. So let's try again. Let's go from our vertex. We're going to go all the way over 1. So normally if we give our input 1, we would expect to get an output of 1. 1 squared is 1. However, I am going down. Let's double check our scale on the this y-axis is 1, 2, 3. I'm going down 3. So normally I would get 1. However, I multiplied by some a value and got a -3. So my a must be -3. Again, every output is being tripled, it's being stretched out, and it's being flipped because of that negative value. All right, so we know we're going to have a times x minus h squared plus k. H in this case is 0. I do not need it. So this is just going to be -3 times x squared and then minus 4. And that is the equation of your quadratic that we graphed there. All right, last but not least, we have this cube root function. Again, it's curving sideways, kind of like our square root function. It's going to move faster because or slower because we're cube rooting it. And then same to the left, we actually get those negative outputs because we can take negative cube root. So for example, the cube root of -8 is -2. So that's how we get that left half as well. So this is a cube root function. The most basic version of that would be the cube root of x. So that's our mother function. All right, so let's identify our locator point. Again, this is a locator point, and it's a locator point because it's kind of that turnaround point. It's not a vertex. Okay, so this appears to be at -3, -3, -3, -3 is my locator point. And then normally, if I were to go over 1, I would go up. If I were to go over 1, I would go up 1, right? But I didn't. I went up 2. So normally we would go over 1, up 1, because the cube root of 1 is 1. However, I multiplied by some a value, and I ended up going up 2. So what would your a value be? 2. So we have our a value, we have h and k, and we're ready to write our equation. We know it's going to be a times x minus h cube. Oh, no, not a cubic, cube root. A times the cube root of x minus h plus k. So our a value is 2. We have the cube root of x plus 3, because minus and negative looks like a positive, and then minus 3. And that is the equation of your cube root function. Again, what you need to do is spend time getting comfortable with the shapes of these graphs. You should be able to identify the shape just by looking at the graph. And then again, you want to find your locator point or your vertex, and then use your mother function and your actual function to determine if you multiplied by an a value and what that a value would be. Hope that makes sense. Have a great rest of your day.